Bayesian inference is a powerful approach to statistical analysis that updates our beliefs based on observed data. Unlike traditional frequentist methods, which rely on fixed parameters, Bayesian inference treats parameters as probability distributions, allowing for a more flexible and interpretable approach to uncertainty. Monte Carlo methods play a crucial role in Bayesian inference, enabling us to approximate complex probability distributions that would otherwise be impossible to compute directly. What is Bayesian inference? Bayesian inference is based on Bayes' theorem, which allows us to update our prior beliefs in light of new data. Instead of estimating a single value for a parameter, Bayesian methods estimate a posterior distribution, which reflects the range of possible values given the observed evidence. Challenges in Bayesian computation. The biggest challenge in Bayesian inference is computing the posterior distribution, which often involves complex integrals that cannot be solved analytically. Monte Carlo methods provide a way to approximate these distributions efficiently. Monte Carlo methods in Bayesian inference. Monte Carlo methods rely on random sampling to approximate complex distributions. The two most common approaches in Bayesian inference are 1. Monte Carlo integration, used to estimate expectations and probabilities in Bayesian models. 2. Markov chain Monte Carlo, MCMC, methods used to generate samples from high-dimensional posterior distributions when direct sampling is difficult. How Markov chain Monte Carlo helps Bayesian inference. MCMC methods allow us to draw samples from the posterior distribution by constructing a Markov chain that gradually converges to the true distribution. The most popular MCMC algorithms used in Bayesian inference are Metropolis-Hastings algorithm proposes new samples and accepts them based on an acceptance probability. Gibbs sampling efficiently samples from conditional distributions when they are known. Hamiltonian Monte Carlo HMC uses gradients to explore complex distributions more effectively. Example: Bayesian inference with Monte Carlo methods. Let's consider an example in medical research. Suppose we want to estimate the probability of a new drug being effective based on prior clinical trial data. 1. We start with a prior belief about the drug's effectiveness. 2. We collect new clinical data and update our belief using Bayes' theorem. 3. Since the posterior distribution is complex, we use MCMC sampling to generate thousands of potential parameter values. 4. The resulting distribution gives us a more refined estimate of the drug's effectiveness, incorporating both prior knowledge and new evidence. Advantages of Bayesian inference with Monte Carlo methods. Handles complex models where direct computation is infeasible. Provides full probability distributions instead of just point estimates. Naturally incorporates prior knowledge and uncertainty into predictions. Works well with small datasets and hierarchical models. Challenges and considerations. Computational cost. Monte Carlo methods require many iterations to generate accurate results. Convergence issues. Poorly tuned MCMC algorithms may take a long time to converge to the true posterior distribution. Choice of priors. Bayesian inference depends on prior distributions, which must be carefully selected to avoid bias. Conclusion. Bayesian inference with Monte Carlo methods is a powerful tool in modern statistics, providing a robust way to update beliefs and make predictions based on uncertainty. From medical research to machine learning, these techniques have revolutionized how we analyze data in uncertain environments. By leveraging MCMC methods like Metropolis-Hastings and Gibbs sampling, we can efficiently approximate complex posterior distributions and gain deeper insights into probabilistic models.